Welcome again to another edition of the Multivariable Calculus screencast. Today we are again discussing Green's theorem here, but we're gonna approach it sideways, and I'll explain what I mean by that. First, let's remind you what Green's theorem is. Well, it all starts with a vector field, and we'll call the components of that vector field P and Q, as usual. So every point in the plane, we've got some vector present, and then we have an important object. We've got some domain in the plane. We'll call that D, right, solid region, and C is going to be its boundary, oriented counterclockwise. Here's the picture that goes with it. Right? So there's the ingredients, really, kind of three things. You have the vector field, right, that's present everywhere in the space. D is a region in the plane, and C is its boundary of that region, oriented counterclockwise. You see it here, kind of moving around this way. Okay, so what does Green's theorem have to say about these objects? Well, it says if we take the line integral around the outside of this region, line integral of the vector field, that is here, it's the same as taking a double integral of this funny function here over the interior, right? So it relates a kind of flow, if you will, of the vector field around the outside to an integral, double integral over the interior, and we have this integrand here, qx minus py. We called it the scalar curl, as you recall. Now, there are a couple other notations that are going to be useful here. In general, for a line integral of a vector field, we can write it different ways. Here are two other ways to write it. One is as a line integral with respect to arc length of f dot t here. So t is the unit tangent vector in the direction of our curve. Right. F is a vector field, and then ds here means with respect to arc length. Handy. And then another way is just to break it up into components here. So use p and q. Right. In our notation, this is exactly the same integral. I'm just going to go around my curve. I'll integrate p against dx, and I'll add it to q against dy. You can kind of see the dot product happening there. P, q, and dx, dy being dotted. So that's well and good. Green's theorem relates the flow of a vector field around the outside of a region. And here we see all the unit tangent vectors right, around the boundary C here. And we're going to take the dot products with f and then integrate all the way around. It says that that's equal to the integral on the inside of our region of this quantity qx minus py that we call the scalar curl. So that is well and good, but now we can ask yet another question. Right? Instead of asking how the vector field flows around this region, I basically want to say, well, how much does this flow through the region? And we can answer that question by looking not at the unit tangent vector, but by doing something clever, and this is the sideways part, taking our unit tangent vectors and just rotate them until they point out. Right? And then ask the same question. If I were to integrate this vector field going along my curve, but instead of taking the tangent vector, taking the normal vector here, I'll call it n, looking at the dot product, the number I'm going to get is going to be sort of the flow of this vector field sort of through my region. Right? And the way I have it oriented here, right, is that if the vector field flows out of the region, I'm going to get positive numbers, right, for my normal vector here, and then where it's flowing in, like say on this surface, I'm going to get negative numbers. So I'm getting an aggregate, right, of the flow of my vector field into and out of my region. So let's see what Green's theorem has to say about that. So let's do some computation. We start with the tangent vector. Remember, that's the derivative of parameterization divided by its length. Right? Remember, so it has length 1, but points in the correct direction tangent to the curve. In components, that looks something like this. The dividing by the length, that's just the derivatives component squared, added square root. And then we have just the plain old derivative r of t up here. All right, so x prime, y prime. Now, why do I spell that out? Well, so remember what the picture is. Here's if I have a unit tangent vector, points in a given region. Now, to do that rotating, to get the unit normal vector pointing out, and I just realized, okay, I need something that's orthogonal to t. All right, so it's going to point out in this direction. And really, if we just switch the components a of b and negate the second one, we'll be pointed in the right direction here, and it's a quick check, like just from our picture to get the signs right. A is negative in this picture, and then so we have a positive y derivative here, right? The negatives will cancel. All right, so b minus a. All right, if I switch my components around that way, I'm going to get the orthogonal vector in 2 dimensions. All right, that's kind of neat, and that makes the whole thing go, because now if I want the unit normal vector n here, now it's going to have the same length, so I divide by that y, and all I need to do is switch the x and y components and negate the second one here. So what this expression is, the parameterized version along my curve of what the unit normal vector will be. Right? And so now computing that flow out of my region is just going to be the vector field dotted with n at each point. And so I end up with a nice expression here. And so just to be clear, how do I find the flow out of my region? I'm going to integrate over c f dot n, and it turns out being, well, so the y prime will end up next to the p, and the x prime ends up next to the q with the negative sign. So this integral is just another form of my flow out of my region. And now I apply Green's theorem, but you got to be careful here about applying Green's theorem. Remember how Green's theorem works. It says, right, that if I have an expression like this guy on the right, I'm going to take the thing in front of the y component, so it's p now here, and I take its x derivative. So here's what happens when I apply Green's theorem to this guy. Right? You really must mind your p's and q's here. So again, remember that Green's theorem says take the function in the I direction, or rather in front of dy. Right. Here, take its x derivative, and then take the thing in front of dx and subtract its y derivative, so the minuses cancel. And I end up with this expression suddenly. So I kind of did 2 switches here. And so what's this? Wait, we've seen that before. That integrand, lo and behold, that thing is the divergence of the original vector field f. So something really did happen here. It says that if I were to take the flow of my vector field out, right, so in the outward unit normal direction here, it turns out it's the same as integrating this quantity, which we call the divergence of f, over the inside. Here. So Green's theorem now can sort of be expanded into 2 results. The original one, this guy here, which we can summarize by saying, okay, if you integrate the curl, right, over a whole region, you get the flow of the vector field around that region, which makes some sense. And now we've got another formulation of the same result. It says, if we integrate the divergence over the inside of my region, I'm going to get the total flow out of the region. And so these are just two formulas, but hopefully get us a greater understanding of Green's theorem.